Hello, my name is Scott Block, and today I'll be presenting CMOS and MEMS co-design. Electronics have worked their way into all aspects of our lives, anywhere from the home front to the battlefield. In the case of warfare, sensors can help gather data to bring situational awareness with minimal risk to soldiers. On the far extreme, sensors can also be integrated into household items such as chargers to help minimize or eliminate wasted power. For sensors on the battlefield, smart dust nodes can be deployed. They are millimeter-sized devices with a few sensors built in, such as audible-based trip sensor and ultrasonic rangefinder, just to name a couple of examples. And back on the home front, nanowatt controllers can be implemented into smart chargers to sense when no longer in use and physically disconnect the charger via micromechanical electro relay. Before diving into those two applications a little bit further and how my research can apply, I wanted to give a little bit of a background where my research first started. When I first came to Davis, I was interested in investigating electrostatic energy harvesting. The discharge here, I generated discharges anywhere from 10 to 30 kilovolts through the means of a really noisy inverter that ran into a transformer and then finally was rectified through half bridge and full, in this case, a full bridge rectifier. But around the same time, I started reading up on microelectromechanical relays, MEMS relays, that were being developed at Berkeley, and was curious about using them for my application. And it happened to be that Dr. Raj was on sabbatical around the same time, and we were able to get a hold of a few. So here's a picture of the first MEMS relay that I probed. You can see the bulk pad here, the drain, the gate, and the source. This is a 4-terminal device. Typically when probing, one of the first tests that I do is I apply a triangle wave from the gate to the body such that it starts to actuate the relay, and then I apply a potential from drain to source. What this allows me to do is figure out the pull-in release voltages. This is the pull-in right here, and the release voltage is here, as well as I can measure the on resistance. In addition, what it does is the electric field from the drain to the source allows for the breakdown of the tungsten oxide on the where the channel makes contact. The MEMS relays during testing actually often failed. They would get weld failures and stick, and so additional information that I looked at gathering was their oxide breakdown. So the way I would do this is I would tie all the terminals except for the gate together, and then decrease the voltage from the gate to the bulk until it started conducting through the oxide. And over here on the left is a video of me actually doing an oxide break. The reason behind probing is the devices were given to us on a wafer here, and the wafer, the streaks between each of the dies actually had tungsten, and this was post-release, so we couldn't dice this, or we couldn't use like mechanical break or dicing to split the dies. But because the tungsten was here, we couldn't actually use lasers to actually cut it either. So we were left with investigating one relay at a time, probing wise. So we looked at some very simple initial architectures that utilized one relay. Let's look at a simpler version of this circuit. This right here is, you can think of this as, it's basically an oscillator, but it's a self-starting regulator. If we ignore the cap CS, what happens is if there's enough potential when the load capacitance is discharged and the Zener reference, this relay will close, start charging up the output voltage. When the potential at the output voltage gets high enough, it will open up this relay, and then it'll stop charging, and then it'll start discharging. So you'll get large ripples like this. Well, the large ripples you see here is because it's the difference between the pull-in and release voltage, and that's what actually determines the ripple. And this is actually where the reference voltage is located at. Another singular, looking at one relay at a time again, we looked at buck regulator. So the buck regulator, you apply a clock to the relay, and so the relay bounces up and down, bounces up and down. This node X right here actually forms a square wave because, well, when the relay is open, the diode ties this guy to ground, because the current wants to continue to flow in the direction towards the output. And then when the relay is closed, this node is pulled towards the input voltage, and so you get a square wave here. And then that's actually passed through a second order low pass filter, and so the output gets smoothed out. Now, depending on your application, you probably wouldn't want to have very large ripple. The relays that I was using, I had to take into account the equivalent series resistance of the inductor, load resistance, and the switch resistance as well. The if we could actually ignore the switch resistance, rho here actually simplifies, and then we're just left with the output over the input is related to duty cycle alone, D here, which is the classic equation that we see for buck regulators. In the case of the buck regulator in discontinuous mode, once again we're applying a clock, but at much lower frequencies, as you can see, 10 and 1 hertz in this case. We still have the second order low pass filter, but the square wave here looks a little different now, because what's happening is during phase 1 we close the relay. Node X is pulled towards the input voltage as shown here. During phase 2, the current wants to continue flowing through the inductor, so it starts pulling it through the diode. So node X gets clamped towards ground right here. But then after a while, the current flow stops through this guy, turning off the diode. And what ends up happening is the node X starts following the output because we have no current flow across here, thus no drop. I did come up with some analytical equations for this as well, but these are solved iteratively, and if you're interested, those are posted in my extra slides. One thing that I didn't show in the last couple of slides is there's actually the relay here is actually a combination of relay with thyristor. Since I was using breadboards, I built the thyristor using NPN and PNP BJTs with their base and their collector, base and collectors connected here. What the thyristor basically does is when the relay is disconnected and the thyristor was on, let's say, then what it'll do is it'll discharge this node until the thyristor turns off. Then when you close the relay, it won't. There'll be probably a tiny bit of charge here, but it's very minimal. And then when you close it, the current will try to start flowing and then kick off the thyristor with some delay. And so what this switching combination is close to basically zero current switching. And what this helped prevent was oxide failure. So here you can see thermal damage because the gate pad is here, and so we're getting current flowing through the oxide somewhere here. And so there's damage here on the relay, and also channel vaporization in this case, where we had too much current running through here and it vaporized the channel. This is probably mainly due to more of a defect. Eventually, since we'd want to put this into smaller packages, maybe multiple die or single die, I also explored the possibility of putting thyristors on a die. This was a TI tape out, a bunch of areas that we could probe, and also several devices that were wire bonded out. Investigation on this die is actually still continuing. Now, going back to using a single relay, the other architecture that we explored is actually a boost regulator. Now, in the case of the boost regulator, what's going on is the Vx is, once again, if it's in continuous mode, you're generating a square wave. Discontinuous, it's a little funky. But basically what's going on is when you close this relay here, it pulls node X towards ground, and then when you open it, the current in the inductor wants to keep flowing, and it switches the voltage, so you get a voltage boost, which will turn on this diode and force current flow onto this low pass RC filter. This R is your load here, so you would get some filtering because of the capacitor here. Now, in this setup, we ran it all in discontinuous conduction mode, and there was exponential behavior noted in the current during phase 1. And if we were to actually run the relay fast enough, reducing this time constant, and if and if we ignore the diode drop, this whole equation right here would actually simplify to 1, and we'd get back to the original known book equations. Now, the input voltage that we were applying in the case of the boost was actually fairly low, that the tungsten oxide would regrow on the channel. So the on resistance was actually changing during operation. And so what I did post-measurement is use what's known as an emulation relay, which mimics the behavior of a MEMS relay using off-the-shelf components. And what I was able to do is I was able to adjust the on resistance of the relay and the pull-in voltage such that it matched with an actual MEMS relay to replicate the behavior, and that's where you got the extra fitted curve. If we go back to here, so you see these black dots here, that's the emulation relay. These red dots are the emulation relay as well, and these red dots here are also the emulation relay. The emulation relay also was great for troubleshooting the test setup before actually probing the MEMS relays, which saved a lot of time in debugging the setup. Now, as I started experimenting with these relays more, I was able to form a collaboration with XCOM, which fabricates through the Army Research Lab piezoelectric relays. So up to now we've been talking about electrostatically actuated relays, and the relays that XCOM uses is piezoelectric relays. I did not design the relays nor the capacitors. I just laid out this spade design, and they created it for me, which was really nice of them. And on this die we have 3 different designs. So on the bottom left and the top right, we have relays where all 4 terminals are just pinned out for the relay. So your gate, body, drain, source. And then in the top left and bottom right, we have relays where there's floating gates. Basically, we put some capacitors here, and you also get access to the floating gate terminal, and externally, you would have to isolate it externally of the die. And then in the middle here, this spade design, this is actually the isolation gate. The actual relay that's doing that has the floating gate is the relay down here. But in the spade design is a combination floating gate relay with the isolation on die. Alternatively, around the same time, XCOM's 3-bit ADC had become declassified, and I was actually able to use it, and they let me lay it out on a die, and we should be getting those back relatively soon, so this is future research. So the MEMS relay research introduced me to a very interesting internship with Chirps Microsystems, where I picked up a variety of other interesting skills, taking whole systems, putting them together, building VIs, learning laser Doppler viometry, which for PMUT testing, which is piezoelectric micromachine ultrasonic transducers. I also learned a lot about different die mountings and I didn't do wire bonding, but learned about wire bonding as well. And then improved my hardware hacking skills as a byproduct. This internship, of course, led to future internships with other MIMS-related startup companies, and started me on some very interesting research related to ultrasonic transducers. So my former colleague and I, Ofer, created a 3x5 PMUD array. This is a monolithic structure where the MIMS and CMOS dyes are eutectically bonded. The really cool thing about this is that the PMUTs have very little parasitics to the actual electronics. So the electronics are buried down between each of these back cavities. And the design that we chose for the ultrasonic piezoelectric micromachine ultrasonic transducers, which is over here shown on the right, is a dual electrode. Now we weren't doing a dual electrode to try to get twice the sensitivity or twice the transmit power. What we were doing instead is we were using the center electrode for transmitting the ultrasound and the ring electrode for sensing, which eliminated the recovery time due to switching, and also allows you to sense the whole time as well as the ring down for sensing the natural resonance of the PMUD. Before going a little bit into the circuitry, let me cover a little bit how an actual PMUD works. So you basically apply a square wave to the transducer, and that starts to excite the transducer and get it ringed up. And as the transducer rings up, it starts to generate sound waves, and those sound waves start to transmit through air. Now here I'm not allowing it to get into mechanical steady state, but killing it before that and then allowing it to ring down. So during the ring down is actually when you can measure what the actual natural frequency of this device is, and you can adjust at what frequency you're driving the device to account for temperature changes. So anyways, the sound is traveling through the air and bounces off an object, and then the returning waves some short time later are picked up by the transducer as echoes. And as the sound travels through the air, it is attenuated due to loss in the air. Additionally, depending on the angle that you received the returning sound from, it may receive some additional attenuation. With our PMUTs, we had a field of view basically of 70 degrees, where we'd get basically a 3 dB loss at each of these corners over here. Of course, you'll pick up a little bit past that, but this was kind of the field of view that we had for a single PMUT and our array. So of course you can't see behind an object, and there's a dead zone due to the ring up and ring down of the PMUT itself, and then there's a dead zone, of course, due to the shape of the PMUT. So how can you compensate? How can you compensate for this attenuation in air? There's what you can do is over time, because you know the loss is basically you know what the loss is through the channel over time. So what you can do is you can compensate by gaining up over time, and then the return echoes will receive that appropriate gain. So here's an example of time gain control. So during the transmit, you set the minimum setting to avoid saturating your front end, since we're always looking at the transmit signal. And then at specific time steps, what I've done is I've gained up the signal, and of course, so you can see the noise here. And this was done with using this setup, which was a four-stage, basically a four-stage amplifiers back-to-back, where you could change the gain on the third and fourth stage. Ignore the clip detect. This is not used for the time gain control for now. So what we would do is externally using an MSP430, just once the transmit signal had been generated, which also went to the MSP430, that sent information to change the gain for these two stages, and then we step through those different gains over time to amplify the returning echo. Now, if you look a little bit more closely at the 4-stage, it's a simple diff pair, a 2-stage operational amplifier, except there is what's known as a clip detect. This clip detect was actually designed by Wesley. I implemented it into the design that Ofer and I came up with, the monolithic structure. And simply what the clip detect does is it detects when the amplifier is close to saturating, and of course it also detects when it's saturating, as you can see here. So what this allows you to do is, instead of doing a time gain control, what you can do is you can, after your transmit, set your maximum gain, and then if clipping happens, lower your gain. Interestingly enough, if you do detect clipping, when the clip goes off, you could actually measure your time very simply. But if the returning echo is too small and doesn't cause clip detect to happen, then you'll have to do some additional processing to actually figure out the time of flight. So the advantage of this, though, one of the big advantages is this is the exact same object, the exact same distance. And this is, if you notice right here on the AGC, it's only a 2x zoom, and this is actually a 20x zoom. And so we've gained it up a lot, except in the clipping section we stopped it. We gained it a little less, and the rest of the time the max gain is still set. So the PMUT project, ultrasonic transducer, also with the work that I did at Chirp and some earlier work in my PhD in low power logic, along with basically stuff that I did in my master's and throughout the whole of my PhD, including my last internship, played into the next project, the N0 DARPA project. We were tasked with designing, basically on the circuit side of things, a wake-up circuit that consumed around 10 nanowatts of power. In this project, we came up with two architectures that we were kind of comparing. Well, they kind of evolved after each other. So there's a synchronous architecture, and then we had two asynchronous architectures that we designed and built. The MEMS sensors that we were using to basically be kicked off when the generator turned on was a MEMS microphone and a MEMS accelerometer using stacked electrodes to increase sensitivity at the expense of load capacitance, input capacitance. So let's first look at the asynchronous front end. There were two versions of the asynchronous front end created. But before diving into those two versions, let me give you a little idea of how this would work. Let's say the accelerometer gets excited, so it's vibrating up and down. And so what that'll do is it'll cause the comparator to, instead of generating two zero outputs, it'll start oscillating at the predominant frequency of the accelerator excitation. The envelope detect, what it does is it basically you receive that waveform, and then it just basically generates a logic high while it's being excited. So so that logic high is then fed into an SR latch. Well, it actually generates complementary outputs. So when it's excited, these complementary outputs are one way, and then when it's not excited, it flips. And the SR latch is actually performing the function of the last requirement, where it's generating a 1 volt signal output flag. So the core of our circuit was actually running at half a volt to save power, and then the very last part was actually running at 1 volt to level shift it to the appropriate supply. So let's start breaking down the asynchronous front end into a little bit more detail. So the first version, built in the TI 180 nanometer process, was AC coupled input on die, and then followed by 4 DC coupled stages, then by 2 pairs of inverters. The first stage looks a little complicated, but basically it's two differential single stage op amps just right next to each other, or one of them setting the common mode, and the other one is actually the input amplifier. And so what's actually going on is these back-to-back diodes are just acting as resistors. And so this common mode is being fed to the input here to the capacitor, and then so the signal comes through here, AC coupled, and then we're sending the common mode via these resistors here. So that's why we're able to do it on die, as we're using the very high impedance of back-to-back diodes. In version 2, I was concerned about because the layout of this guy was quite large. You're talking like 0.7 millimeters by 2-3 millimeters across. Each one of these operational amplifiers was huge, and so I was worried about die mismatch. So on the second version, I AC coupled all the stages. I also made it programmable because we didn't know actually how many stages there were, and I set the common mode for each pair of amplifiers. I also one thing that I didn't do, and I wish that I had, is the default setting. The lowest gain setting you could use is the first two amplifiers. So one thing I wish I had done is gained access to the first amplifier alone, but that was something I didn't do. The envelope detect, let me explain first a little bit how the envelope detects. In the first version, basically what it is the comparator. If you remember back, if we look back at the comparator really quick, is the common mode for each of these comparators is set lower than the trip point for these inverters. So if the amplitude coming out of the comparator is not large enough to switch the logic, then we see two logic zeros on the output of the comparator. So we see two logic outputs on the input of the comparator. That's why we're using NMOS here, so we get a negative VGS, really turning off these devices. And so we have basically a volatile piece of memory here that's constantly being drained off. So this capacitor's charge is always being drained off by this current source over here. So if we don't have a signal, then what happens is this node gets pulled towards ground, and then we'll see a complementary output of of S being low and R being high. Now, as soon as we get a signal that's large enough, it'll pull this capacitor up towards VCC, the supply voltage, and then flip the outputs, the logical outputs. And here's an example of those curves. So basically, this red line right here, if you look right here, this is the volatile memory node. Now, as you notice, it doesn't actually go all the way up to the supply because you're going from a device that's basically saturated to cutoff. And you can see a little bit of ripple through the first inverter, and then the second inverter not so much, and the third inverter none at all. And then, of course, you see approximately linear decay due to the current source on the capacitor. Now, in the second version, I reduced the size significantly for a few reasons. One of the is I used higher threshold devices for the inverters. So these guys were really long. I mean, they were the inverters themselves were pretty skinny, but they were very long devices, and the layout that I did on them, so they ended up being close to like 0.7 millimeters tall, the total inverter, which is huge. These guys were tiny in contrast, like by a factor of 70. Also, I got rid of the current source here. In the first version, we were aiming for 150 picoamp current consumption for each of the drains, and these guys were close to 0.5 millimeter long. Of course, I chopped them up, but it's still a very large square. And the back-to-back diodes, I think if I remember correctly, I used the 36 in parallel, so that's much smaller than the area that was consumed by this current source. So this design was much more condensed, and it performed basically the same performed the same way, except instead of having a linear decay, you have an exponential decay. Okay, so the last thing. So, so the back-to-back diodes, when using them with a low enough voltage, are actually fairly linear. One of the downsides to the process that we're using, the models are not well reflected of the parasitics. So if you have a large enough negative supply, then you'll start to bias the substrate, and that's what this is indicating right here. The very last part of the asynchronous front end is a level shifter, and the level shifter is basically just a modified SRAM cell that with the cross-couple inverters are being used at a higher supply to generate the 1 volt flag at the output. The other thing I didn't really talk about is the way the current source was being generated for the asynchronous circuits is just using a Weiler current mirror. I used the V-star method to figure out the lengths of the device that are needed in order to generate the 150 and 300 picoamps for versions 1 and 2 respectively. And externally, we would put a resistor or bias voltage to actually try to adjust the current of the Weiler current mirror. In order to minimize the leakage current, the current lost through the startup circuit, I stacked several diode-connected NMOSs so that during steady state there was very little current loss through here. Now let's switch over to the synchronous front end. MEMS devices, of course, would be hooked up externally on this because this was done on a different die. We weren't taking advantage of the InventSense process here. Also, the feedback capacitor was placed externally as well, as you can see up here. In essence, what's going on here, we have a strong arm latch that's fed through, basically there's a negative feedback that's going on, and so we're generating a reference signal. And if there is no signal here, we still have noise. So no matter what, we always have noise. So the output oscillation of Q and Q bar would be dependent upon the frequency and the oscillation of the integrator, depending on which one's a little bit more dominant. So if this was more dominant, then you would oscillate at the at that point you'd be able to actually figure out how sensitive your strong arm latch is. So the slower you run it, the more sensitive it is, but at the same time takes longer. Well, basically you're pushing lower the well, okay. So basically what's going on here is what you're doing is you're trying to push the noise up towards the natural oscillation of the the clock frequency. So if the noise is dominating, then what will happen is the decisions here will be fairly random, close to the period of the clock frequency. If the noise is not dominating and this is not as sensitive and the integrator is dominating, then this should still be much higher than the frequency of interest that you're wanting. So what happens after that is you pass that through a variable shift register, and that gets filtered out. So now when you have a slow varying AC signal that falls between kind of the natural integration frequency of the oscillator and its ability to follow that signal. So if you go too slow, the integrator will just follow the signal and it'll look like there's nothing there. But if the signal's fast enough, basically what will happen is the integrator won't pick up on that, and then you'll get long periods that are related to the frequency content of the input. And so basically what you're doing is when there's no signal, is you're trying to push that towards the clock so that you can filter it out easily. This is a circuit that's still being worked with. So let's look at the strong arm latch. The strong arm latch is basically cross-coupled inverters where I pushed the tail source current mirror actually to both sides of the latch. So what we're doing here is we're actually manipulating the VGS of each of these current mirrors to give more rail-to-rail output swing from the latch. So if we use the current source at the top, because we're always trying to pull current no matter what, we're not really manipulating the gate to source voltage on that guy. We don't get rail-to-rail swing. So I had to push that down into each side of the the latch at the expense of matching. So I had to over-design this GATA to make sure that each half would match quite well. But the thing that I was trying to do with this synchronous version versus the asynchronous version is force all the analog stuff into just one stage, so I wouldn't have to worry about cross-die matching, and it would go right away into the digital domain, and then that would be much easier to kind of manipulate. And so when the strong arm latch resets, it resets low. Its outputs are pulled high. And so what I did also is I put a couple of inverters here, which provide a little bit more gain to really make it a true logical decision, and that's fed into an SR latch, which you want to pull low to hold. Now the logic style that I did for the rest of the blocks after the strong arm latch are actually what I'm calling switch current logic. So what you have is you have two current mirrors between the pull up and pull down logic, and what's happening is as you control the input voltage to this gate, you're increasing the absolute value of the VGS on one guy and decreasing the absolute value on the other guy. And so in fact what you're doing is you're turning one of the current mirrors more on and the other one more off. So it's forcing more current to go out, and at the same time it's turning off the top guy, so you get more drive, more bang for your buck, but at the same time it also pulls very well. And so the gate voltages are fixed, and so what you're doing is you're manipulating the source voltages, which increases the drive steering. So interestingly enough, with this type of logic, you actually want to design the inputs here minimum size in order to maximize the frequency, which is actually defined by the current mirrors and their load capacitance. So, so if you want to run this faster, you just put more current mirrors in parallel to a point. The input impedance, the output impedance of this guy is dominated by these current mirrors. And in fact, in the design that I had, they were several orders larger than the pull up and pull down networks. So the logic threshold voltage VM is actually dictated by these current mirrors, and so you can adjust this very well, very ratioed by how you define these current mirrors. Of course, that's not process independent, because if you have PMOS that are running faster than NMOS, that'll shift where your VM is. But nice thing is you do have a way of ratio controlling it. Also, interesting fact about this is because the current mirrors are so large in contrast to the logic, the size is dictated by the current mirrors, and so the inverter actually becomes the worst use of area and power consumption, because you would actually want to have your pull up and pull down logic blocks as complicated as possible, because you can fit a lot of basically you can fit a lot more logic for the same area. And so, for example, instead of like running through a whole bunch of like 3 different logic gates, if you were able to condense that logic into one logic gate, you would effectively reduce your leakage by a factor of 3, which is actually pretty cool. So how does this all tie to what I was originally talking about in the beginning? Let's first smoke where I was talking about smart chargers and smart dust node. Let's first focus on the smart charger. So the smart charger, the idea here would be to develop a flyback converter where you replaced each of the switches with MEMS relay by itself, or a hybrid solid-state circuit with MEMS relay. Place MEMS relays in key locations in the controller, maybe on the other side of the circuitry, in order to, like for example, the feedback circuitry, to minimize or remove leakage. And then finally replace the controller with a nanowatt power controller. So the idea is that even in standby, your current consumption would be very, very, very low. Now, one thing that I didn't mention very well before is the pull-in and release. The pull-in voltage actually is dependent. So the pull-in voltage can be scaled to lower supplies, which then you can eliminate level shifters and power wasted in those, which is actually really neat. Now, effectively, you could most likely eliminate this nanowatt controller if you were to set up a self-oscillating relay based on certain criteria where it would actually regulate itself to actually kick on, and then it would kick on the circuitry. So in essence, you could, in theory, make a zero current and standby charger. Now, in the case of the smart dust node, what's going on here is you're covering an area of a battlefield with all these tiny miniature sensors just scattered about. And in this proposed design, you'd have a fairly large ultrasonic transducer that you'd be using initially at off resonance. So the wake-up sensor would be set to look for particular patterns or just large enough amplitude off resonance from the PMUT in the audible range. So the idea is that you'd be looking for like footsteps, truck movement, stuff like that would kick off this guy. And so once the nano wake-up circuit kicks off, that'd kick off the rest of these devices. So it would turn on probably the power regulation, the control logic, and of course the ultrasonic transmit and receive, as well as the burst transmit of the short-range RF. So in the case of the power regulation, since the application, well, you probably could get away with some low-frequency regulation. So you could do, in theory, all the regulation with MEMS relays. And of course, feedback that information using a flash ADC, as has been proposed in this work. Now, in the case of the range finding, you could get away with using the ultrasonic transducer setup that we have with the work that Ofer and I did. And since it's used for short bits, it still could be fairly high power. You can also implement the automatic gain control to try to maximize the return signal. In addition, you could actually use relays for the driving of the PMUT if you were able to operate them at the appropriate frequency, because then all you'd have to do is pull the relay to ground. But at worst case, this is only on for a bit, so this could be a bunch of high power inverters, amplifier, whatever. And the last part, the nano wake-up circuit, we developed several different versions of that. Of course, more work would need to be done, and more geared for the smart dust node, curtailed to that. But the idea here is like I was stating before, is within the audible range, use the same membrane that you're using for the distance measurement from the ultrasonic transducer, but use it in the audible range, where when a large enough signal comes, it basically actuates the comparator, and then that wakes up the rest of the stuff, the rest of the circuitry. And then you transmit the ultrasound, figure out the distance, then that's relayed to some central node, and then that gets transmitted further back to base to let the people know what's going on. And interestingly enough, you might be able to do, in this low power wake-up circuit, you might be able to do some initial rough characterization of possibly what the sound is. So I'd like to thank the guys at UC Berkeley for getting me access to the MEMS relays, Texas Instruments for a thyristor tape out and a nanowatt front end, Chirp Microsystems and PicoSense for all the experience I gained from them that was used very heavily, especially in my last research project. XCOM for the future work and relays that are coming. Of course, ARL, Army Research Lab, for producing them. InventSense for the several ultrasonic tape outs, as well as the N0 tape out for the a microphone and accelerometer, and of course DARPA for the funding for the N0 project, and IBM for the tape out of one of the nanowatt, the synchronous nanowatt front end. And finally, I'd like to thank the members of the MEMS Lab and MCSG, former and current, as well as my family. If you have any questions. feel free to ask.